Good morning, everyone. Can you hear me?
Good morning. Yes.
Okay, good. Okay, so there will not be lab today like the regular lab we used to have. We'll be using the lab period to do treat some questions, okay? Kind of revision on everything we've learned. And then I know that some of us don't attend the Wednesday lab, so some of us will be busy. We'll also find a way to make quick to upload the video for the revision class. We may not use the whole 3 hours because we'll be solving some questions. We have just 50 minutes plan to study or solve or teach. Okay, unless we'll make it very interactive such that some of you can also share your screen and get to solve problems for others to see. That was why I wanted it to be in person, so that we'll be coming to the board one after the other to solve. But we'll see how we navigate that after the class, okay? And then I'll post it as information also, so you check out the news forum for that information, okay? No, it's going to be online, not in person. All right. Okay, so today we'll be looking at the second part of the chapter 5 lecture. I uploaded or updated the document or module. I'm going to update it for the last class. I've updated it for this one because some slides were missing in that first one. Okay, so please download the updated version from Moodle. You also have to download the updated version before the third contact. I'll also notify us on what to do with that. Okay, so let's go to what we have today. Today we'll be looking at, the chapter 5 is handling, applying the forces we've learned in chapter 4 to solving physical problems. And we have looked at the first contact, how we use some forces to solve problems. So today we'll be looking at the normal force, the frictional force, and the drag. Those are the 3 forces we'll actually be focusing on in today's class. Okay. So a quick reminder of what we have learned before about the normal force. We emphasize that the normal force is always directed to act normal to the surface of contact. By that, we mean it is always at the perpendicular position or direction to the surface of contact. For example, when we look at this figure here, we see that the normal force from the free body diagram, the normal force is perpendicular. You can see the perpendicular direction of the normal force to the surface, which is this table. Okay, so that always describes direction of the normal force. It's acting normal to the surface of contact or perpendicular to the surface of contact. And a striking thing about the normal force that we should note is that the normal force will always adjust itself such that the object will stay on the surface without penetrating the surface it's sitting on. Okay, the normal force is mostly seen in object at rest or resting on another surface or in contact with another surface. It's a contact force. So we remember in our last class when we used the example of sitting on a spring, so that you not fall into the spring, the particles of the spring will have to compress together to give you a pushback. such that the person will not penetrate into that surface. So for every surface in contact for normal force, that is what happens. Okay, so this key factor is what we should note in solving problems with normal force. That is going to always have to adjust itself such that the object will stay on the surface without penetrating. Okay, so we see the book that is resting on this table remaining on the surface because even when there's a hand pressing further, it could not penetrate into the table because the atomic particle of the table has to compress to give an equal resistance to make the book sit without penetrating. So let's quickly look at an example how this applies to our everyday life. Example of normal force. So we see a 1.2 kg book lies on the table. You press down on the book from above with a force of 15 Newton. The book weight is 1.2 kg. What is the normal force acting on that book from the table? You know that the normal force from this description is going to act perpendicular to the surface. All right. So we'll have a pictorial representation of that description here. The book sitting on the table, then the hand pressing hard with a force of 15 Newton on that book. The book did not penetrate because the particles of the table has to adjust itself to prevent that. Then we use our usual method of identification of forces. We identify the forces in contact with this book. We have the force from the hand, pressing from above, and then the normal force. We have the range force, the W, the weight, acting on the book as well. So we'll proceed to make a free body diagram of this. And what the free body diagram does for us is to help us know for sure the direction of these forces acting on this object, and then to get the value for the component forces. Okay, so from our understanding of resolution of forces or the composition of vector, we'll be able to get that values. We apply these two knowledge, which we have been applying in previous examples to solving this problem. The question is, what is the normal force? We have our parameters, weight of the book and force acting from above. Now, because the book is at rest, it's not moving, we know that it is at static equilibrium, right? So if it's a static equilibrium, we apply the rule that the net force acting on it is going to be 0. So if we bring that into Newton's second law, we'll see that the F equal to A will be 0. Okay, because acceleration is going to be 0, so it will make the whole equation 0. So taking the component, the S and Y component, we can see from the free body diagram that there is no S component, no force acting on the X axis. Okay, so every of our, the summation of Fs will be Ns, Ws, Fs, which is all going to be 0 because nothing is in that direction. So that is why we presented only the Y component expression. So the summation of all the forces acting on this book, which is normal force, the weight, and the force from the hand, is equal to 0. So looking at the value of each of the component forces, N, which is normal force, is acting in the positive direction, upward. Weight is acting downward, and the force from the hand is also acting downward. So we'll have minus, minus to represent the direction as we know. The question asks us to look for N, which is the normal force acting on the book. So if we bring out this equation, we're going to have that N is equal to, this will cross the sign of equality to be W plus F. Okay. Now the value for F is given. We have to look for the value for W. So from weight force formula, W is equal to mg. We know the constant value for G to be 9.8. And the mass of the book is given as 1.2. So we just apply that to solving for W, multiplying 1.2 times 9.8 to get 12 Newton. So we have the value for W, we have the value for F, which is the force pressing from the book. We just substitute straight into this formula to get the final normal force to be 27 Newton. Okay, so if you put that into this, you will see that the net force is going to be 0. So that's how we apply normal force to solving problems. Now, having seen normal force, we want to look at another one, which is the frictional force. Okay, if an object is actually at rest, what happens if another force is acted on it and it starts moving or try to move? Okay, the force that is pressing down this book is not pressing in the direction to make the book move. It's pressing in the direction to make the book penetrate, which the force of the normal force will not allow that for such description. The book cannot penetrate the table at that force. Okay. So, but let's visualize a woman pushing a bus, and before the woman can successfully set that box to go in motion or slide, it's going to go through several stages of frictional force. Okay. So we take the first case, visualizing the woman pushing the bus. We see the woman applying the force to push. We have we did a body identification approach, making a circle round. So we'll have our contact forces to be the frictional force, but the type of frictional force here is static friction. Why is it static? We said that we'll have two types of frictional force, static and kinetic frictional forces. One acts when the object is not moving, and the other is acting once the object begins to move. Okay, so the frictional force is dominant at this stage when the woman is just pushing, but the bus does not move. It's not moving. So what is happening in this case is the woman is giving a gentle push. The frictional force pushes back gently, such that the frictional force, static friction, is equal to the force of push at this stage. Now, if this woman pushes harder, the frictional force tends to return back harder as well to resist the motion of the bus. So the woman pushes harder, the frictional force resists, but the bus still did not move. It remained at rest. So we still have a scenario where the Fs is still equal to the force of push. Okay, so the bus is still moving. Now, if that woman now happens to add, push harder, add force, more force to set the ball in motion, it will get to a state before the bus starts moving that the frictional force will resist. Remember, the direction of the friction of friction is always opposite to the direction of motion. So we see the push direction going forward and then the frictional going backward. Okay, so it will get to a time just before the bus will start moving that the frictional force will get to a maximum strength. and we notify that stage as F max. Okay, so the frictional force at maximum magnitude. So at this stage, before the bus starts moving, while it is at rest, all the net force has to be 0. So before the bus starts moving, it gets to this maximum stage, and the woman applied higher force to set the ball in motion. Once the bus begins to move, the frictional force instantly converts to the static friction instantly converts to kinetic friction. Okay, so now the magnitude of the static friction will reach that maximum value before it just gives in. That is the push force of push over have to overcome that maximum value. So static friction value is always going to be not less than or equal to the static frictional maximum value. Okay, so the static friction maximum value is proportional to the normal force acting in this case or any object. So with this constant of proportionality, we now have this expression that static friction mass is equal to the product of the constant of proportionality times the normal force, which we identify this to be the coefficient of static friction. Okay, so this is basically the general formula for friction. The frictional force is going to be the product of the static coefficient of the friction times the normal force. So once the bus starts to accelerate, it's no longer a static friction. We have to now look at a different kind of frictional force, which we have identified to be the kinetic friction. Now, for the kinetic friction motion to obey the law, that is Newton's second law, and it has to be the kind of motion that we will recognize as to be in dynamic equilibrium. Okay, so let's also keep assuming that this woman added more push, and then the bus started gliding or sliding along the surface. It moved. We made the free body diagram of that motion. We see that the kinetic friction applied here is opposing the force of push in the S direction. Then we'll have the normal force acting upward. Then the weight acting downward. So the kinetic frictional force is the same no matter how fast the object glides or slides on the surface. It's going to be the same. So kinetic frictional force does not depend on the speed of that object. So we say that the kinetic frictional force is nearly having a constant magnitude, okay? Because it does not depend on the speed. So we have the expression that the kinetic friction is also proportional to the normal force. We always have this expression about friction. Now, we did not mention in our catalog of forces when we describe that friction is of two parts, kinetic and static, because this another kind of friction that we identify here as rolling friction behaves exactly the same way as kinetic friction, which is the friction that exists for objects in motion. Okay. Now, the only reason why we introduced the word rolling friction is because we are using it to describe the different type of motion that object will take. It is easier to roll an object than to slide them over surfaces. Okay, but we'll have cases where we have object we have to slide, and we'll have object that we can roll. So we'll bring in another concept of rolling friction, which acts exactly like the kinetic friction, okay? The same expression is what we use to state that the rolling friction will also give us the product of the coefficient of friction times and the normal force. Okay, so let's see. This formula is what was applied to different materials having contact with one another. We see the rubber on a concrete, experimentally calculated the static friction to be this value, the kinetic friction and the rolling friction to be that value. We see that the coefficient of friction for these three different types of frictional interaction gave us different values. So it varies also for different materials. But in solving problems, most of the time we specify the particular kind of, or we specify the value for the coefficient that is being, coefficient of friction that would need you to apply. Okay. So we'll look at example of that with friction. But first, before we look at an example, we want to see how we'll be working with frictional forces. Okay, you can come on the mic, Shamaka. You have a question. I see your hand is raised.
Yes. Do we need to memorize the coefficients?
No, you don't have to. It will be provided.
Okay.
Okay. So there are already standard values, and whenever we are asking a question, most of the time it's stated in the question or given as the constant to work with. And in the last class, somebody was asking if I'll be providing a kind of equation sheet or table. I'm considering doing that. Okay. So what we are emphasizing is actually the ability to apply these things. You don't have to memorize most of these things. Okay. So let's look at how we work with friction. With frictional forces, because we have different type of frictional force that will give us different values, we'll have to learn how to work around these three type of frictions. But to do that, we're going to quickly look at the summary of all the model frictional force that we have. We have the static, kinetic, and rolling friction with their symbols, Fs, K, and R. Now, the static friction will always take the direction necessary to resist the motion. Same applies to every other friction. They will always take the direction to oppose the motion. But to work with this friction, we still apply the same method that we used to know, which is if we establish that the friction is a kinetic, once we establish the type of friction, we also establish the type of state, whether it is in static equilibrium or dynamic equilibrium. Then we follow the strategy we used to know, identifying the forces acting on the object, and then we apply it into this general equation. If it is static, if it is the kinetic, here will be K. If it is rolling, the symbols will change, but it's also follow the same pattern. So when it's a static friction, we use this formula, but once the system starts gliding or moving, as it slides relative to the surface, we know that it's a kinetic frictional force acting on the surface. Then we apply the Newton's second law to solve the problem to obtain the normal force. Now, it's not always going to be the question saying obtain the normal force. Any of the parameters can be determined as long as you have the question and the provided information. So I put up here that equation 513, but this, my apologies, this is actually equation 510, which is what I've already put here in this tab, okay? So we'll apply these three equations to solving problems. We will do that also with the understanding of the Newton's second law and the resolution of forces or decomposition of vector. So if it is rolling or sliding or at rest, we know the particular equation to pick and the coefficient of friction to use will be provided. So let's quickly see An example. Carol wants to move her 32 kg sofa to a different room in the house. What did she do? She placed the sofa slider on the sofa. Then the sofa slider is a slippery disc that will help Carol quickly roll or move this object to a different location. This value here is not mk, sorry. It is actually mu k. Because the sofa is in motion, we identify that it's a kinetic friction. So the sofa coefficient of kinetic friction here is given as 0.08. So after she placed the sofa slider under the feet of the sofa, she then pushed the sofa at a steady, see the word steady speed of 0.4 meters per second across the floor. How much force does she apply to the sofa? So we did the identification of forces of her action. She's going to be pushing, we are assuming that it's moving to the right, okay? So if she pushes to the right, the kinetic friction is going to oppose that motion. So from our free body diagram, we position these two. The action is happening on the x-axis. But on the y-axis, we see the range force and the contact force that is acting on this object. That is normal force and the weight. Okay. So if we assume from this statement steady that this is moving at a constant speed, it means that this motion is in dynamic equilibrium. And immediately we establish that, we should automatically apply the fact that the net force will be equal to 0. Okay, so we'll bring out all the forces acting in the S and Y component. For the S component, we will see the normal force, the weight, the force pushing, and then the kinetic frictional force. Those are the forces, 4 forces present in this motion. Now for the x-axis, we'll have only these two will be 0. We have only the force of push and the kinetic friction. From this expression, we see that the force of push is going to be equal to the kinetic friction. So if the question is asking us to determine the force applied, the information of the kinetic friction will also help us to find this because they will be equal to each other. So that is the information the S expression supplied to us. So we'll move to the Y. We'll have the Y component of the normal, the weight, the force of push, and the kinetic friction to be N minus, N is positive, W is always acting downward, to be equal to 0. Therefore, N is equal to W in this case. All right. So if we pick the vertical motion, which is the motion on the y-axis, we see this expression, which will eventually give us the N being equal to the W. From the weight force formula, we have that W is equal to mg. Remember the weight, the mass of the sofa was given to us. So apply that, we know the constant value for G to obtain our N. This is the given coefficient of friction. So we'll substitute that into our understanding of the first expression, which is the force of push being equal to kinetic friction, which is also equal to MA. Now, from the frictional force, Fk is equal to mu k n. Now, if this is true, we already know what n is, so we can substitute n to be mg. So substituting for N in this equation of friction, we'll have mg being N, put it here. Coefficient of kinetic friction multiplied by the mass multiplied by the constant G. Substituting directly, we have the force applied by Carol to be 25 Newton. So we see how we played with the information supplied, understanding of resolution of forces, and using the equation we established in the working with forces, because we already know the type of frictional force to use to obtaining this, okay? So we have other examples that we did not look at, but we're just picking one under each discussion just to buttress our point. Now, we have been talking about friction, friction, friction. What actually causes friction? Whenever two objects are in contact, what happens is that the high points of that object will be making contact with each other such that it will always have to undergo a constant collision, deformation, and a brief bond. Okay, so we see the microscopic view of what happens when somebody steps on a surface. Okay, this is exactly what happens. The high point of the shoe touches the high point from the table. So they make contact such that they'll undergo, those points will undergo collision, deformation, and brief bonding before the person leaves the leg to move. All right. So we have established that from this kind of interaction, which will always apply, the frictional force is proportional to normal force. Then when you remove the constant of proportionality, which is recognized as coefficient of friction, we'll have this expression. So each of the kind of friction will always carry either S, F, or R, okay, as the case may be. Okay, we'll look at the last part of the forces we'll be looking at today and how we apply them on in our everyday life. The last one is the drag force that we want to look at today. We have already established in our previous classes that the drag force is that force that retards motion or opposes the motion of object moving through fluid. The fluid can be any substance like water or air or any other substance. But the things we should note about drag force is that it's going to oppose the direction of velocity. It goes in opposite direction to velocity. See the man on the back moving, the velocity vector will move this way, then the drag is opposing the direction of that velocity. And what you have noted as well is the fact that an increase in the magnitude of drag force, increase in speed, will give an increase in the magnitude of drag force. Like we saw earlier in frictional force, the woman pushed harder, the frictional force tried to increase to resist it. So every kind of force that resists motion tend to increase once the velocity of that object is increasing. Okay, but to better understand how we apply drag force to solving problems, because we have varieties of fluids in nature, we have to introduce another term we call Reynolds number. Okay, we have done experiment with drag force in the lab, so I want to expect that anything we're going to say about drag force is something you have already interacted with experimentally and applying once you have solved the assignments on that exercise on that lab sheet that was given to you. So to understand how to apply drag force in situation, we had to introduce what we call the Reynolds number. All right. So, but what is this Reynolds number that we introduced? Remember, we emphasized that because we have varying types of fluid, We have air, we have water. Each of them will have different resistance rates to motion. We had to introduce that to understand how we can actually apply this in solving natural or physical problems. So Reynolds number simply is the ratio, not the word ratio, of the inertial force to the viscous force. Because we'll be talking about drag force, we know that whenever an object is moving in fluid, remember viscosity, which is the quantity that expresses the magnitude of the internal friction between object and the fluid, between the object moving through that fluid. Now, if we say Reynolds force is the ratio of the inertia, remember inertia is that force, that ability to resist the change in velocity or to resist motion for that object. Whenever an object is moving, for example, the experiment we did in our lab, although you didn't go physically to the field, but that is what happened. Whenever an object like the car is moving through air, it's going to push aside the fluid, that is try to overcome the drag to advance. But the drag force will also act on it, okay? So we express this statement mathematically as inertial force over viscous force, that our Reynolds number is with the symbol Re, which is equal to the density, this is the velocity, and the L is actually the size, which is usually specified in question as well, over the expression of viscous force, which is the air viscosity, the L, and the V. When this cancels this, we have this final expression as the formula for drag force, okay? And what the formula for Reynolds number. And what we should note about Reynolds number is that it is dimensionless. It has no unit, so you don't have to worry about what is going to be the value if you're asked to calculate or determine the Reynolds number. The information that the Reynolds number provides to us is to tell us the kind of drag force that is present in any interaction, okay? The motion of an object moving through fluid, is it actually, is the inertial force is dominant or the viscous one? So this ratio, which is the Reynolds number, helps us to determine that. When the Reynolds number is high, it means the initial drag is dominant. For us to say Reynolds number is high, it means the Reynolds number is greater than 1000, which is typical of most tangible object, that is object that we can easily see, like the car, the motion of a racer, somebody riding a bike. Those are the dominant one. The inertia, force of inertia, which is the force practically dominant in the motion through air. But whenever the Reynolds value is low, we see that the viscous force is dominant because that fluid is thicker than the air. That is what it tells us. Okay, so we have the high Reynolds number, the low Reynolds number, we have the intermediate, but in this test, we are just going to look at the high and the low. We'll leave the intermediate because the application of that is complex, which is beyond our scope at this level. Okay, so let's take a quick example. Consider a 75 millimeter diameter baseball moving through a 20-degree air at a speed of 20 meters per second. We can take the ball characteristic size, which is our L, to be the information of the diameter that is provided. Okay, so it means that in applying it to the equation, we're using the information of the diameter provided as the size. So we want to determine the Reynolds number of this motion. So putting that into this equation, we know the density of air, which is the viscous value, sorry, the viscous value, the density of air, the volume, the speed, which is given, the L, convert the millimeter to meter, then I call this thing mu, or nu, which is the air viscosity. It's a constant value. It's usually provided. You don't have to memorize it, okay? So applying that straight into the formula, we see that the Reynolds number is 100,000. This is already greater than 1,000. So we consider this value obtained as high Reynolds number. So it agrees with the statement that it is an operation in the air, okay? So considering drag with high Reynolds number, the general formula for Reynolds number is this. But when we want to specifically apply drag with high Reynolds number, that formula is modified a little to what we see here. Okay, so we'll have that automatically tells you that when we want to apply it to low Reynolds number, it's also going to follow a different modification as well. Okay, so we'll have the value for high Reynolds number, which is the drag, considering it in terms of high Reynolds number. Drag in this case is going to be half. This is, we call this the coefficient of drag, which you determine that the last practical, if you tally it with the equation given to you, see it's the same. So we'll have half the coefficient of the drag coefficient, then the density of the fluid, the cross-sectional area multiplied by the speed. Now what this is saying is that the drag of a system with high Reynolds number is proportional to the square of the object speed. The drag, all these are constants. So the drag is going to be proportional to the square of the object speed. So let's see how we apply this to an example. We have just 10 minutes to look at 4 more slides. The biologists have estimated the drag coefficient of a swimming penguin by observing the rate at which the penguin speed decreases in its glide phase when it's not actively swimming and is slowing down. In one study, these are the parameters the biologist documented from his observation. A gliding 4.8 kg Gen 2 penguin has an acceleration of minus, which tells you automatically the direction. Sorry, this should be up. It has acceleration of minus 0.2 meter per second. When, if you have a question, you can raise your hand and I'll allow you to come to the mic, okay? So when the speed is 1.2 meters, if the frontal area is given to be 0.02 meters squared, what is the penguin's drag force, drag coefficient? Okay, so we want to assume that this penguin is moving along the S direction, all right? And then if it's moving along the S direction, we already know the acceleration, the velocity direction. It is specified that the penguin is slowing down, okay? So you should understand the direction of the velocity from that statement and the direction of the acceleration. That is what led to that value we had, okay? And this is typical to the kind of experiment you did in the last lab. When the vehicle was slowing down, the value of acceleration you got was negative, all right? For a slowing down object in motion. So with that understanding of our second law, which is force equal to MA, and we have assumed that it's moving on the X axis, where the S component of the drag is negative because it's pointing to the left. It's pointing to the left, the S component is negative. Then we solve the problem using the magnitude of drag force provided in our question. So we have minus MS is going to be equal to the mass given to us in the question multiplied by the acceleration. We'll obtain the force to be 2.5 Newton. Remember, the question asks us to determine the drag coefficient, which is this value. So to look for the drag coefficient, we had to make it the subject of formula in this equation. Okay, so making the drag coefficient CD the subject of formula, we have 2D over the density times area V squared. The density of water is 1000 kilogram per meter cube. Okay, we'll have the area, frontal area specified in the question, and then we'll have also the speed also specified in the question. So we substitute directly into the formula to obtain this coefficient. The drag coefficient does not also have units. Okay. All right. So we look at before we proceed to looking at the drag at the low Reynolds number, because we have seen the drag at high Reynolds number. We want to look at another term that we'll be introducing or using to understand that. We call that the terminal speed. The terminal speed actually applies mostly to falling objects, all right? So the falling object speed will increase until it reaches a point where we term it terminal speed. Let's take the three examples here to understand that. We see that at low speed, the drag is small and the ball falls at acceleration approximately equal to the acceleration of free fall, which is g. But what happens when the motion continues? The two objects have the same size. If the two objects have the same size and shape, or have varying size and shape, the more massive object kind of has a larger terminal speed. That is, it quickly gets to that speed, which is that stage that will say it is terminal speed, which we have defined as the speed when the net force acting on that object becomes 0. Okay, so for this case, we see the ball. At the beginning, the two of them has the drag on this ball, the velocity all pointing down, has about the same value as g, which is the coming from the drag from acceleration from the gravity, the pull of that object to the earth. But as the speed increases, the drag kind of increases as well. The net force and the acceleration gets smaller. It starts decreasing, slowing down. All right, we see the speed is increasing, but to get to a stage where the drag and the weight tend to be equal. So the net force on this system becomes 0. At this stage, we say that that object is at its terminal speed. All right, it has gotten to that stage where the net force is 0. So for every falling object or object that is falling, it speeds up and then get to a stage where the net force acting on that system is 0. At that stage, we say the object has reached its terminal speed. Okay, that is what we mean by the more massive object has a larger terminal speed, tend to reach the terminal speed at a larger rate than a smaller object. Okay, so an object falls at constant speed with 0 acceleration. From that, immediately an object reaches a terminal speed, it starts dropping with zero acceleration. It means that the object is actually dropping or moving at a constant speed. Okay, so that is what we mean by terminal speed. So when we use the word terminal speed in solving problem or in a statement of problem, it means that we're referring to that state of that object when the net forces on it is 0. And this mostly applies to falling objects, okay? So now the reason why we had to put that in is because we use that word in the last example that we'll be seeing today, okay? So for high Reynolds numbers, like we saw in the case of low Reynolds numbers, the formula for high Reynolds number is for the drag is B, the viscous value, and then the V, okay? So the B is given as to describe the size, the shape, in the first case, we're using L. For the B, for Reynolds number that are small, the drag force of the motion, especially in fluid, we have the expression of V, the drag force being proportional to V. In the other case, it was proportional to the square of the velocity. All right, so substituting the value of B into this equation, we obtain this drag force for, which always mostly apply to shapes that we can describe as sphere. All right, drag force of a sphere becomes 6 by nu, then RV. This is the viscosity, which is the nu, the radius of the object being described, and the speed, pi and c, they are constant. Now, at this case, whenever the Reynolds number is less than 1, we say that the expression or the kind of drag is linear. And the linear drag on a sphere is described with what we call the Stokes law. Okay, so we see how that the understanding of frictional force and drag helps us to explain the Stokes law, which will be seen in our other chapters. All right, so the force needed to propel a sphere to its terminal speed, which we have explained earlier, to bring that sphere to a state where the net force acting on that system is 0 and it begins to move at constant speed, is described with this equation of drag force. Okay, so this same force is expressed as the drag force in terms of terminal speed. That is why we have the V terminal. All right, so when we don't have it as that stage that the object is already at terminal speed, this remains drag force of a sphere. All right, so the last example, which is the very last slide, I know it's almost time. If you have class, you can go. It's a straightforward example. We just substituted all the parameters given in our questions into existing formula that's given to us. Now notice that we use the terminal force here because in our question, it was specified that this motion is actually, the polling green actually got to the stage of terminal speed. All right. Okay, so that I will not take the time of everyone. Do we have question, comment on whatever we have discussed so far or concern about the class we'll be having in the afternoon? Hello?
For
Dr.
this,
Kennedy.
is this review in person or just online through this link?
Yes, we're going to use the same link and review will be done online. Now we're supposed to meet in person, but if we meet in person, we'll spend the 3 hours on that revision. My idea was to have us meet in person, but if we meet in person with a group of or a set of us in the class, that means we'll be meeting in person on Friday. So if I meet in person with you today and don't meet in person with the group for Friday, that will be partial on my side. Don't you think so? So that's why I concluded that it's best it's online. We'll take the first 15 minutes, then I'm compiling some practice questions, which is not, it's just going to be typical of what you receive, but not exactly. If we look at few examples, we just spend 15 minutes, then you have the freedom to study because the test will cover chapter 1 to 5. Okay,
Okay, thank you.
thank you. Does any other person have comment? Please look at this example that we did not detailedly look at in class. It's because I know when you read the question, if you have any question about this or other examples that we did not look at in the test, be free to send me a mail and I'll reply you, okay?
I just want to double check, which chapters did you say the midterm was on? I just missed it.
1 to 5.
1 to 5. All right, thank you.
Yep, you're welcome.
Also, there's a question in the chat and it says, when will you be posting the lectures to YouTube?
Okay, I'll do that today. Before the close of work today, I should do that. Okay, someone said doesn't have a mic or a camera. Or camera for the laptop. So, okay, actually, if we met in person, how the format of the class would have been, we put a question, everybody brings their feedback on the question, the kind of formula we would have used to solve the question, then we'll solve it on the board or have someone to come to the board to solve it. So first, we're going to be looking at the solution for your assignment, which will be typical of what some of the questions will be seen in the exams. And we'll have the multiple choice question, then the written part. The multiple choice question, we have been seeing multiple choice questions in our classes. It's not going to be different. Some multiple choice questions might be calculations that you just do. And that is for the exams, not in this. I don't think I'm going to do that in this first test. So we'll just solve few questions. It's going to be questions that you can finish in 50 minutes. All right. So since we'll not be meeting in person, we'll just interact for 50 minutes because it's mostly going to come from my end. It would have been interactive, but some of us already have this excuse that we don't have laptop camera. Laptop screen cannot write, like we don't have screen that we'll be able to write on. But if you do, I'll be glad to have you share your screen to solve it. Okay.
Just a question, not talking about like class today, but just about the midterm. Like, what is the format of like the questions going to be on the midterm? And are we doing it online or in person, or how's that working?
We're doing the midterm online. So we'll have different persons under different invigilators. So it's what you need to have is a clear desk. Then somebody's putting already that doesn't have a laptop camera. If you do otherwise, we'll have to assume that you're going to retake the test because you did not follow all the certain rules with the test. So please, if you have a friend you can get a laptop or with camera from, just get it and use it for that 15 minutes, okay? The 15 minutes will just be about an hour, so you return the person's thing. So if you don't have, you have an ample time to seek to get one for the test, please. So the camera will be focused on you. Once you begin, you're not allowed to move. Don't give me the excuse of I'm going to ease myself. It's going to be a straight 50 minutes that you prepare to be on your desk. Okay, so if you have any medical condition that will make you have to not be able to sit for straight 50 minutes, do let us know and we'll find alternative place for you to take the test. We'll have some persons that will be invigilating in person because of special cases. So if you have any reason to appear in person, to be invigilated in person, just let us know. Okay.
Okay, so when is the test? On Wednesday or Friday?
The test, because I did not have any persons giving me excuse for it not to be Wednesday, it's going to be on Wednesday. Or would you prefer it on a Friday? Do you want to take the test before your weekend?
Personally, I prefer it on Friday.
So why didn't you say? I gave the opportunity to say or state your preferences. How many persons seconds the Friday opinion? Our date is still very flexible. Before we stamp it, do we want the Friday or the Wednesday?
Wednesday is fine because then we can get it over with, I think.
Okay. Friday. We'll have persons on either one. Okay. I'll post the exact date for the test today. All right.
Sorry, I'm a bit confused. So we have a test and we have an exam as well, like a midterm.
Yeah, it is the midterm that I'm calling the test.
Pardon?
It's the same. I'm just using the terms interchangeably. It's just one midterm exam.
Okay,
First midterm exam. That's what I'm calling your test one.
okay, sounds good.
Okay. All right.
For the midterm, like what's the formatting of the questions? Like how, how many of each kind, I guess, I don't know.
So we'll have two set of questions, the multiple choice and one you have to write, then you solve. You can either solve on your tab, solve on any device, then you can that you can upload once the test is ending. You upload it on, I'll create a place or platform like the assignments, but this would be midterm. Then you upload the written solution or written on or typed. You know, we have some of us have systems that we can type, then write on it. Whatever system you have, let it be such that at the end of the test, you just upload. Okay.
And how many multiple choice questions are there and how many like of the long answers are there?
We're looking at okay, I'm looking at in 15 minutes what you can cover in 15 minutes. So I have sets of 40 multiple choice and 10, but I'm still going to have to solve to see if it's something that we can cover in 15 minutes. So it's something that you can cover in 15 minutes that I'll put there. Okay, but just make up your mind that you will have a number of multiple choice and a number of theoretical questions.
All right, thank you.
Thank you.
Do you think you would be able to maybe like upload like a Word document, just kind of going over the steps of how the test is going to be? That way it makes it a bit more clear for everybody.
Yes, I will.
Okay, thank you.
Thank you. All right. The test is going to be simple. It's not something strange. It's not something you've not seen, okay? Just do your best and success is certain, all right? All the best, everybody. Bye-bye.
All right, thank you. Goodbye.
Thank you.
Okay,
Bye-bye.
bye.